Welcome to the Explainer. So glad you're here because today we're unpacking something absolutely fascinating. Have you ever been totally amazed or maybe just incredibly frustrated by how AI enhances images? If so, you are definitely in the right place. We're diving into a groundbreaking paper from ICML 2026 by Hongbo Wang and an amazing team. It's called Coloring the Noise, Adversarial Sobolev Alignment for Faithful Image Super Resolution. Okay, I know, that title is a total mouthful, but don't sweat it. By the end of this explainer, you're going to know exactly how this team is literally changing the way AI reconstructs our visual world.
We absolutely have to start here, because this is a universal problem. Why does AI hallucinate when fixing images? You know the drill. You feed an AI a blurry photo, maybe a face or a landscape, and ask it to sharpen it up. And it does. It looks super crisp at first glance. But zoom in, and suddenly the skin looks like smooth plastic, or the tree leaves turn into these weird repeating geometric blobs that literally don't exist in nature. The AI just straight up made up fake details. Well, this paper zeroes in on exactly why that happens, and more importantly, how to mathematically stop it in its tracks.
To make sense of all this, we're going to break things down into 5 quick parts. 1. The super resolution problem. 2. Why AI hallucinates details. 3. Coloring the noise. 4. The ASSR framework. And 5. Results and structural fidelity.
All right, section 1, the super resolution problem. Let's dive right in and set the baseline for what we're actually dealing with here.
Image super resolution, or SR, is basically just taking a low-res, blurry, or pixelated image and blowing it up into a crisp, high-res masterpiece. Now, modern AI does this using something called generative priors. Think of a generative prior like the AI's massive memory bank of what the world usually looks like. But here's the catch, and the authors point this out as a massive flaw. While these priors make really pretty pictures, they often totally fail at faithful restoration. The AI basically cares more about making the image look good than making it mathematically true to the original source.
So we end up with this massive clash. Authentic, high-frequency details versus AI hallucinations. We want the real grit, right? The exact pattern of pores on a cheek, the chaotic scatter of gravel on a dirt road. But when the AI doesn't actually know what's missing, its generative prior just takes a wild guess. It paints over the blanks with what it assumes looks right. So you end up sacrificing the actual truth of the photo for an artificial, completely made-up lie.
Which brings us to section 2, why AI hallucinates details. Let's look under the hood. Why is the AI guessing so terribly wrong?
The authors pin the blame on something they call spectral misalignment. I know it sounds super intimidating, but let's break it down. Imagine the AI is throwing darts at a target. The AI's mathematical goals, the isotropic objectives, are perfectly round and perfectly uniform. But real-world images, the intrinsic natural image manifold, they're not uniform at all. They have a really messy, complex geometry. So because the AI's round peg goals and nature's square hole reality don't match up, there's this massive geometric gap. The AI is literally looking for the wrong mathematical patterns.
Here is the best way to picture this. A lot of models today use spectrally flat Gaussian noise. Think of that like old school, completely uniform TV static. It's totally random, right? But real images don't look like TV static. They have natural spectral decay. That basically means the big, sweeping shapes and colors dominate, and the tiny, high-frequency details kind of naturally taper off. If you train an AI using flat TV static, it completely loses its mind trying to tell authentic, tiny details from pure hallucinations. It's just blinded by the flat noise.
Moving to section 3, coloring the noise. This concept is the real game changer, the actual bridge to solving the whole mess. So the absolutely crucial point is this. We have to change the noise. If flat static is blinding the AI, the authors say we need to explicitly color the noise transition kernel. In signal processing, colored noise just means it's not totally uniform. It has a specific frequency. By coloring the noise so it perfectly mirrors how real images naturally decay, boom, the AI is finally training in an environment that matches reality. It can actually see the difference between real grit and a fake hallucination. To pull this off, the paper shifts the whole generative process into a space governed by Sobolev-induced Riemannian geometry. Okay, yes, that is some incredibly heavy math. But you don't need a math PhD to get it. Just think of this geometry as a highly specialized sandbox. By dropping the AI into this exact sandbox, they're forcing it to play by nature's structural rules, not the artificial rules of flat TV static. It's a total paradigm shift.
Section 4, the ASASR framework. Now that we've got the theory down, let's look at the actual engine they built to make this happen.
Say hello to the adversarial Sobolev alignment for super resolution, or ASSR. We can boil this dense process down into 3 really elegant steps. Step 1, recast the generative flow. That's moving the AI into our special geometric sandbox. Step 2, color the noise to match natural frequencies. And step 3, well, this is where it gets spicy. They integrate a parametric adversary. Basically, they bring in a challenger to actively fight and test the AI.
This adversary runs on something called the Riesz Representation Theorem. For us, you just need to know this theorem is the absolute powerhouse engine driving the adversary. It ensures the adversary's attacks are perfectly aligned inside that complex Sobolev sandbox we talked about earlier.
And this is just brilliantly clever. Instead of the AI just trying to paint a pretty picture, the parametric adversary actively generates targeted negative samples. It calculates the worst-case Sobolev gradients. Actually, let's put that in plain English. It finds the exact mathematical weak spots where the image would look totally fake and fall apart. Then it shoves those plausible failures right in the AI's face. The adversary is essentially the harshest grader ever, constantly showing the AI exactly what not to do, which brilliantly steers it back to authentic, realistic details. Section 5, Results and Structural Fidelity. Let's see how this all pans out in the real world. Does ASSR actually deliver? The short answer? Yes! Big time! The authors ran extensive tests, and ASSR totally outperforms the leading generative baselines. Thanks to that colored noise and the harsh adversary, it preserves spectral consistency beautifully. It keeps the structural fidelity totally intact, so the physical architecture of objects actually looks real. And best of all, for those of us using these tools, it effectively crushes those weird, plastic, hallucinatory artifacts we all hate. Let me just read this directly from their conclusion, because it really hits the nail on the head. ASSR outperforms leading generative baselines, particularly in preserving spectral consistency and structural fidelity. They basically set out to close the massive geometric gap between AI math and natural image structure, and they absolutely crushed it. Which leaves us with this final thought. If we're finally moving past the era where AI just guesses and slaps fake pixels everywhere, what is the future of truly faithful AI generation? Once AI models perfectly align with the actual geometry of reality itself, the line between a digital reconstruction and absolute optical truth completely vanishes. Imagine the impact on medical imaging, on satellite surveillance, or even just saving your own old family photos. Perfect clarity is coming, and it's going to be mathematically perfect. Thanks so much for hanging out with me for this explainer. Keep asking those big questions, and I'll catch you next time.